into the details of working with numerics in Python, I thought it would be valuable to review just some basic principles about numbers. And the most important concept to start with is that there are multiple types of numbers that each arising from different uses that generated them. So we essentially have integers that come from counting and real numbers that come from measuring things. And this is a summary from Keith Devlin, who's a math professor at Stanford. And there are more than two types of numbers, and Peter Alfeld, who is a math professor here at the University of Utah and one of my favorite professors that I ever had, has a description of more types of numbers. Python has three distinct types of numbers, and so we'll kind of review the number systems that are most closely associated with numeric types in Python. So first off, we have the natural numbers, and these are numbers that relate to ordering and counting objects. So the set of natural numbers is denoted by the symbol n, and definitions may vary in whether they include 0 or not include 0. But again, here the main idea is that we're counting things, or we're ordering things. Integers come when we include 0 and negative numbers. So these concepts date back to the 9th century. The symbol for integers is Z from the German, I'm not a German speaker, Zahlen, meaning numbers. And integers are essentially what we have in Python when we are working with an int type. So Python has, the integers have negative and positive values as well as 0. When we talk about NumPy, we'll see that we can define arrays that don't include negative values, and so in that sense they're closer to the natural numbers. Rational numbers are denoted by Q, arise from making measurements, and they're the ratio of two integers. And then we have the real numbers. And real numbers come from measurement processes, and it's kind of an interesting history behind real numbers, which I have some references here too. Real numbers we can think of as positions along a line, indicated here, and lots of interesting, like I said, lots of interesting history that's associated with the real numbers. The next set of numbers that aren't as common in most of the applications that you would run across in biomedical applications are complex numbers. And whereas we thought of real numbers as a position along a line, complex numbers can be thought of as a position in a plane. And I've got just some details here. Complex numbers actually do come up a lot in signal processing and especially image processing, medical image acquisition, where MR signals are what is measured in the MR scanner as a complex number, and then they are manipulated to create the images. And complex mathematics forms the basis of CT reconstruction, also for an example. But for most of the application, unless you are doing medical imaging or signal processing, complex numbers won't be a big part of your life. But I happen to love complex numbers, and so I can't have a class where we're not going to at least make sure students are aware of them. The next kind of idea that becomes important in programming is that while these sets of numbers, the natural numbers, the integers, and the real numbers are infinite, we can't represent infinite numbers in a computer. And that's because we have to allocate bits, which are essentially transistors in the computer that are going to represent a single digit in a binary mathematics system to represent parts of the number. And so we have to make choices of how large of a number that we're going to have represented in our system. And as we went over in class, Python provides a max size, and this is the largest number that can be represented in hardware by the computer. And you can read up on the details of this if you're interested. Now, an architecture, computer architecture like mine, the underlying computer is using 64 bits of information and moving data around between memory and the CPU, all using a 64-bit architecture. And so we can use 64 bits to represent a number, but typically we have to represent a plus or a minus sign. And so we usually have 63 bits that we can encode the magnitude of the number, and then 1 bit is reserved for the sign or the polarity of the number. Floating point numbers are a much more complex concept. The important thing to keep in mind about floating point numbers is that they are inherently approximations. And so I have some links here to more detailed articles about the limitations of floating point numbers, and this nicely titled "The Perils of Floating Point Numbers." Again, the key idea here is we are always approximating the floating point numbers. The Python provides some variables that will allow us to determine the nature of the approximation. And so just like we had a maximum size, I gotta come up here, it looks like I don't, wait a second. I need to have an import sys here, that there's a maximum floating point number that we can represent, a smallest floating point number that we can represent, and these are magnitude concepts that can be negative. And then this epsilon this is the smallest difference between numbers that Python will be able to recognize. Any calculation that we do that might have a difference of values less than this are not going to be detected in our Python code. And finally, I just have a link to a website that talks about the different thinking, just keeping in mind the difference between categorical numbers, ordinal numbers, interval numbers, and ratio measurements. That is, are we talking about numbers that just represent an order, and there's not like an actual difference, magnitude between the numbers in the sequence? Intervals would be where there's a fixed spacing between the spacing between numbers have meanings, and ratio is their spacing between numbers has meaning, and there's a true 0 point in the system.